We have been looking at the root locus method for getting some idea of the transient response of the feedback control system or even open loop control system, and we saw that some of the ideas associated with the root locus can be used to determine the value of the gain beyond which the system may become unstable. Now we will look at another approach to the same problem, which is based on what is called frequency response. Historically, the root locus method was invented in the 1950s, whereas the frequency response approach to the feedback control system analysis and design was developed in the 1930s and 40s. As I told you earlier, people who are working with telephone networks first came across this problem of stabilizing of amplifiers, and Harold Black invented the idea of, or rather applied the idea of feedback to stabilize amplifiers. And because of this, people who were studying amplifiers till that time started looking at feedback in amplifiers, and this is how the frequency response method was developed. In the case of an amplifier, whether it is used for speech, which was the main application, transmission of voice signal over long distances over a large telephone network, this was the first application. Today, of course, one can talk about other communication networks, wired or wireless. Now, in these applications, frequency response is a very important concept. A signal being sinusoidal is a very meaningful signal. For example, a pure tone, if one looks at it on the oscilloscope, looks like almost a perfect sinusoidal signal. And parts of speech also look like periodic waveforms, and therefore we know from Fourier series approach that it can be thought of as consisting of a number of sinusoidal signals. Because of this, it is quite natural to think of frequency response when studying amplifier performance. And so the frequency response techniques were developed in the 1930s and 40s for not only studying the performance of amplifiers, but also studying the effect of feedback on the behavior or the performance of amplifiers. So we will take a look at it now, although it seems that the root locus method, which was invented later, does a better job for this purpose than the frequency response based analysis or method. Now we will start with a very simple result, which is as follows. You have all studied functions of a complex variable in your mathematics courses. So suppose z is a complex variable, that is z stands for any complex number whatsoever, then you might have a function of z which is also a complex number, that is, it is a complex valued function of a complex variable, and typically in the maths courses the symbols z and w are used for the two complex numbers. So w equal to fz represents what is called a mapping or a transformation of the complex plane into the complex plane, and in order to show this diagrammatically, one shows the two numbers z and w, start with the complex number z, apply the function f to it, you get the value f of z, that is another complex number w. So these two numbers z and w are shown in two different planes, that is, you think of, instead of one single complex plane, you think of two different complex planes. So one is called the z plane, the other is called the w plane. So let us say here is the z plane. In other words, in this plane or in this part of the diagram, I am going to represent the complex number z, and here is the other plane, let us say we call it the w plane. That is, in this part of the diagram, I am going to represent the value of the function at a complex number z. So for example, if I choose a complex number z here, it may be some complex number like, let us say, 2 plus j3, right. It is a complex number in the first quadrant. Of course, I have not put the real and imaginary axis headings here. So if I do that, this is the positive real axis, this is the positive imaginary axis for the z plane. Likewise, I will have the real and imaginary axis that is the real and imaginary parts of w in the w plane. So, let us say there is some function f such that its value at 2 plus j3 is, let us say, minus 1 plus j3. So, where is the point minus 1 plus j3? Well, that will be a point somewhere here. Here is the point minus 1 plus j3. The real part is minus 1, the imaginary part is plus 3. And so, one says that this point 2 plus j3 is mapped into the point minus 1 plus j3 under the function or mapping f. And this function or mapping f will do different things to different points in the complex plane. Different points in the complex plane will be mapped in the complex plane z plane, will be mapped into or taken into different points in the w plane. And one uses this terminology of mapping. Z is transformed into w under the action of f, or f maps a point in the z plane into a point in the w plane. So, this is the way in which one looks at such functions and what they do to complex numbers. Now, let us consider a very simple complex function, namely w, which is fz, is simply given by, let us say, z minus 1. So, if I start with a complex number z, then what this function f does to it, it simply subtracts from it the number 1, and I get a new complex number, and that is the value of the function. It is a function as simple as that. Now, let us look at the following. Here is the z plane. In the z plane, I draw a simple closed curve and a very special one. I will draw what is called the unit circle. So, suppose this represents the unit circle in the z plane. What does this mean? To say that this is the unit circle in the z plane, it means that it is the set of all points z such that modulus of z is equal to 1. This in a way is the equation of the circle, unit circle in the z plane, mod z equal to 1. So, here is a point which is on the unit circle. So, here is the complex number z, and here is the corresponding vector drawn from the origin to the complex number z, or this vector can also represent the complex number z. Then the modulus of this z, which is the length of this vector, must be 1. And so, all the points which lie at a distance 1 from the origin will satisfy this condition, and conversely, any point satisfying this condition must lie at a distance of 1 from the origin. So, this is a curve in the complex z plane. It is a simple closed curve, and you should go back to your complex variables or complex functions course and find out what is a simple closed curve. Now, one goes a little further. One thinks of tracing the curve or moving along the curve in a particular direction. For example, I will put the arrow here this way, which means now I am going to trace the curve or move along the curve in the counterclockwise direction. Now, such a curve with an arrow on it, which indicates the direction in which you want to trace the curve, is called a contour. So, I have chosen a contour in the complex plane, and it is conventional to use the Greek letter capital gamma to denote any such contour. So, in this particular case, I have a closed curve gamma in the z plane, which is travelled along or traversed in the counterclockwise direction. So, I have this curve, but there is a direction given or marked on it, which is the direction in which I am going to travel around the curve, as it were, or traverse, direction of traverse in the counterclockwise direction. Also, it is clear from the figure that if you were to sort of move around this curve, and at the origin you had some mark or some pole or something, then from the figure it is clear that as you move around the curve starting somewhere and you come back to the same position, you have gone around the origin through one revolution. Because it is very simple to visualize that, because you can think of this radius vector, and as you move around the curve, the radius vector will go on turning, and if you move around the curve once starting at a point, move in this particular direction that we have chosen and keep going till you come back to that point, at the end of it you would have completed one full revolution in the counterclockwise direction around the origin of the z plane. So, one says that this curve gamma, with its direction along which it is supposed to be traversed, encircles the origin in this case once in the counterclockwise direction. Or one says that this curve gamma with this direction of traveling around it, the number of encirclements, this is the terminology that is used, the number of encirclements, the number of times the point, the origin is encircled, the number of encirclements in this case is exactly 1. Now, this is very simple for the circle, but it is not much more difficult for a different curve. So, let me take another example. Let me draw another curve. Here is my curve gamma now, which is no longer a circle, and here is the arrow which tells you, this arrow tells you that you are going around this curve in this direction. Now, what is the number of encirclements of the origin by this curve? The curve is no longer a circle, but I can still talk about the number of encirclements, because I can think of this radius vector whose length is going to change as one moves around the curve, but as one completes one traverse of the curve, the radius vector will have moved through 360 degrees in the counterclockwise direction. And as you know, counterclockwise direction is taken as the reference direction in the complex plane field, and therefore the number of encirclements will take it as 1. So, in this case, this curve gamma encircles the origin once, and when you say that, you mean once in the counterclockwise direction as you traverse the curve gamma in the direction which is shown on the gamma. Let us take one more example. Here is this curve gamma, and I traverse it in this direction now. What is the number of encirclements by this contour or curve gamma of the origin? It goes around it once, but in the clockwise direction, and therefore we will count the number of encirclements as -1 rather than +1. So, in this case the number of encirclements was +1, and in this case now the number of encirclements is -1. So, the number of encirclements will not just be a number, but it will also have a sign, and essentially what matters is the direction in which the curve gamma is traversed. For example, the same curve gamma, if I traverse in the opposite sense, then the number of encirclements will be +1, whereas if I traverse it in this sense, then the number of encirclements will be -1. So, the number of encirclements depends on this direction of traverse or movement around the simple closed curve. Let us take one more example. Here is the closed curve, and I traverse it, let us say, in this direction. Now, how many times does it encircle the origin? So, what do I have to do? Think of a typical point on this curve, think of the radius vector, and think of the point moving, or think of yourself as traversing around the curve in the chosen direction. See what happens to the radius vector. In this case, you can see that the radius vector is going to move this way, but then is going to move back, then it's going to move this way, then it's going to move back. So, what will be the total change in angle or the total rotation of the radius vector? The answer, as you can see, is going to be 0 degrees. The radius vector is going to move in the counterclockwise direction, but then it is going to start moving in the clockwise direction, and then it will again move in the counterclockwise direction when it gets back to the original position. So, the rotation of the radius vector, total rotation from the beginning to the end, is 0 degrees, is through an angle of 0 degrees. So, the number of encirclements is 0, and of course, visually it is very clear the origin does not lie inside the closed curve, and therefore, you can explain that the number of encirclements by this closed curve of the origin is 0. So, the number of encirclements can be 0, the number of encirclements can be a positive number, or the number of encirclements can be a negative number. So, given any simple closed curve in the complex plane, we can immediately talk about number of encirclements by the closed curve of the origin. Now, what is true of the origin, one can apply for some other point. For example, here is the simple closed curve, and I can talk about the encirclements by this closed curve of this point, which let us say is -2 plus j1. What do I have to imagine then? First of all, of course, I need a sense or a direction for moving along the curve, so I am putting that arrow there. Now, think of a radius vector going from there to there, from this point around which you are trying to find out the number of encirclements to a point on the curve, and imagine what happens as the point moves along the curve. Now this radius vector is again going to swing back and forth, and the total rotation of the radius vector when this point has moved completely around this curve will be 0 degrees, and therefore the number of encirclements of this point by this simple closed curve will be 0. Once again, it's obvious that this point is not inside the curve, whereas if I had a point here, let's say, which is inside the curve, and now I wanted to calculate the number of encirclements of this point by this closed curve in the same direction of traverse, then you see the answer will be 360 degrees, or number of encirclements will be +1. And of course, we see that this point is inside the simple closed curve. So all this is very simple. In fact, that's why the curve is called a simple closed curve. But we can make the situation more difficult, and this is because such a thing will happen when you deal with a transfer function, or when you deal with a system which has poles and zeros, maybe more than one of each. For example, let me draw another curve which is not a simple closed curve. Here are the axes for the z plane, and here is a curve that I am going to draw. Of course, I have traced it before you. So if you remember that, I start from here, then I go here, here, then here, here, then here, then here, then here, and then I come back. Because there are these intersection points, so it's not very clear which way I am going, but I am telling you how I have gone from, say, this starting point A, and I have come back. Starting from A, go this way, and now not come here, but go this way, go here, now go not go this way, but go this way, go around here, then come here, then not go this way, but come here, then not go this way, but come here, and then come back to A. Now this is not a simple closed curve, it's a closed curve, because I have come back to the starting point and I have moved continuously, there is no break in the curve, but it's not simple any longer, because as we can see, the curve sort of intersects itself in a number of places. There is 1, 2, and 3 points of intersection. So this is not a simple closed curve. But if I say now how many times this simple closed curve encircles the origin, what is the answer? Well, what do I have to do? Think of a typical point here, draw the radius vector from the origin. We are interested in encirclements of the origin. So draw the radius vector from the origin to a point on the curve and start moving along the curve. See what happens to the radius vector. Now you can follow and see that the radius vector is moving this way counterclockwise first, then it will move clockwise again, then it will move counterclockwise, then clockwise, then counterclockwise, till it finally comes to the old position A, and the total rotation of the radius vector will be through 0 degrees. The total angle, the net angle, meaning positive and negative are to be counted as separate and to be added up. So the net rotation position, the total change in the angle is 0 degrees. So the number of encirclements by this curve of this point, the origin, is 0. And again we see that this point, the origin, lies outside this simple closed curve. Now what is inside and what is outside is not really very clear, and that is why one has to sometimes go through this exercise of imagining a point on the curve, this radius vector, and then trace the point on the curve, see what happens to the radius vector, how does it swing back and forth, and whether it swings totally through 0 degrees or through an angle which is different from 0 degrees. This is what you have to see. Let me draw one more figure. I will draw a similar looking curve. So I will start with that, and here is that curve, and being traced in some particular direction starting with a point A. And now suppose I have a point P here. Now I ask, what is the number of encirclements by this closed curve, say gamma, of this point P? Now is the point P inside the curve or outside the curve or what? It's not so easy to answer, because the curve itself is not simple any longer. It is intersecting itself in 3 places. So what is going to be the number of encirclements? Well, we start the same way, draw this radius vector from this point P. We are interested in finding out how many times the curve encircles the point P. So start with this radius vector and let A move around the curve, see what happens to the radius vector, see what is the total angle through which the radius vector turns. Now if you do that carefully, what will be your answer? As I go from this position to this position, the radius vector would have turned through 180 degrees in the counterclockwise direction. As I go further from here to up to this point, it would have gone through a further 180 degrees in the counterclockwise direction. Of course, it will coincide with its initial position PA, but the net angle will be 360 degrees in the counterclockwise direction. Then it starts from here, let's say, and continues further. So counterclockwise all the way till this point is reached, when 180 degrees has been completed, continuing further another 180 degrees in the counterclockwise direction. So the total rotation of the radius vector will be 720 degrees in the counterclockwise direction. And therefore, what is the number of encirclements by this curve gamma traversed in that direction of this point P? The answer is 2. 720 degrees divided by 360 is 2. 360 degrees is one rotation, that counts as one encirclement, but it is 720, so the number of encirclements is 2. Now, when the curve gets more complicated than this, and sometimes it can become more complicated, there are a number of intersections, then how do you work it out? For example, I put the point P here, so let us call it P dash. Now, what is the number of encirclements of the point P dash by this same curve gamma? Now, I can do it the same way, of course. Draw the radius vector from P dash to A, imagine going around that curve, see what happens to the radius vector, and then follow the change in the position of the radius vector and figure out what is the total rotation of the radius vector, the total angle through which the radius vector has turned in the counterclockwise direction, divided by 360, that will give you the number of encirclements. Now, is this point P dash also inside the curve or is it outside the curve? Now, someone may say it is still inside the curve, but if you find out the number of encirclements of the point P dash by this curve, then your answer will be 1 and not 3 or 2 or 0. Now, I will ask you to go through this yourself. In fact, you can draw, copy this figure, put the point P dash, actually take your ruler, or as I have done it, use your finger or your ball pen or whatever, and literally sort of trace the variation, trace the movement of the radius vector as you go around the curve, and ascertain for yourself that the net rotation by this curve or by the radius vector, the net rotation as the point traverses around the curve is through 360 degrees, and therefore the number of encirclements is 1 plus 1 and not 2 or 0 or minus 1 or whatever else. Now, there is a way of finding this out which is sometimes useful, and that is the following. From the point P dash or P or whichever point around which you want to calculate the number of encirclements, draw what is called a ray or a half ray. That is, draw from it just a line which goes away towards infinity. Such a line, if you remember your geometry course, is called a half ray. And of course, I can put a point arrow on it to indicate that I am going from P dash out to infinity along this direction. So, such a thing is called a ray. Now, when you have such a half ray, then this half ray can intersect the curve in 1 or 2 or 3 or 0 points. For example, if I have a point here and if I draw a ray this way, then this ray is not going to intersect this curve at all. Whereas from this point P dash, I have drawn this half ray. This half ray does intersect the curve in 1 point. Now, at the point of intersection, you have to figure out which way the movement of the point is taking place, point on the curve. The point on the curve is moving in the counterclockwise direction. So, count that as plus 1, and this is the only intersection point, and therefore the number of encirclements is plus 1. I can do it with another half ray. For example, I draw this half ray from P dash going in this direction. Okay. Now, this half ray intersects this curve in how many points? There is one point here, there is another point here. Well, actually it looks like two coincident points here. Okay, the way I have drawn the figure and drawn the ray, why not? Now, for each intersection I have to find out which way the movement of the point on the curve is taking place around P dash. Now, when I take this point of intersection, the curve is being traversed this way, so the movement around the point P dash is in the clockwise direction, so that is minus 1. Whereas if I look at this point, there are 2 points actually twice intersecting. So, one of the intersections is, let us say, this one, then when I move along the curve this way around the point P dash, I am going in the counterclockwise direction. So that's plus 1. Then I come back here and now I move along this part of the curve. Again it is counterclockwise. So plus 1. So plus 1 and plus 1, that is plus 2, and this one is minus 1. So the total is plus 1, and that's the number of encirclements by the closed curve of the point P dash. This is a little more convenient or easier than drawing the radius vector and then imagining the radius vector to turn around and then figure out what is happening to that radius vector, what is the net angle through which the vector turns when it comes back to its original position. For example, with this point now, what is the number of encirclements? I can draw any ray. So in particular I have drawn this ray. Well, this ray does not intersect the curve at all, and so the number of encirclements is 0. Now I can draw a ray which does intersect the curve, and I can go through the same rule, and you will find out that the total number of intersections may be more than 0, maybe 1, 2, 3, whatever it is. But if you use this rule, that is counterclockwise plus 1, clockwise minus 1, for each one of the intersections and add up, you will get the number 0. For example, here is a radius vector that I am going to draw like this, starting from this point. It has how many intersections? There is one intersection here, another intersection here, a third intersection here, and a fourth intersection here. So there are 4 intersections, but the number of encirclements is not 4. I have to find out what it is. Now for these 2 intersections, whereas these 2 intersections, this one and this one, are both in the clockwise direction. So minus 1 and minus 1, that's minus 2. So the net is 2 plus minus 2, which is 0. So whether I draw the ray this way or draw the ray this way, I will get the same answer. In fact, that's why this method will work. And so you can draw a ray which is convenient so that the number of intersections is as few as possible, and then from that you can figure out the number of encirclements. So although it looks like a very simple idea that you have a closed curve and you have a point in a plane, the closed curve is also in the same plane, then you imagine a point moving around that closed curve, and the radius vector joining the point on the curve to the fixed point therefore moves. What is the number of encirclements by this curve or the point that is moving on the curve of the other point? Think of yourself standing on some ground at some point, and the closed curve may be something that is marked on the ground, the periphery of some region, it may be a boundary of a field or whatever it is, and think of somebody moving, physically moving along that curve, and as you stand here, you turn your head, keeping your eyes on that person, in other words looking at that person, and then as the person moves around the curve, you have to turn your head, and sometimes of course since you cannot turn your head by a very large angle, you may have to turn your body. So essentially you really can count the rotation that way and see how many times that person has gone around you. This is the simple idea of encirclement of a simple or not a simple closed curve by a simple or not simple closed curve of a point. Now this is a very useful idea, and although it looks very simple, it is not really that simple. And the examples that I have taken are such that can actually occur in our calculations. So simple closed curves is not the only thing that you will come across when we use this for our study of the effect of feedback on control system performance. Okay, let me get back to the problem then. Here is the z plane, here is the w plane, and I have a simple function w equal to fz, where fz is given by a simple formula z minus 1. Now I choose to start with a simple closed curve in the z plane, and let's go back and again choose the unit circle and trace it in a particular sense or direction. Let's say I have chosen the counterclockwise direction. So as the point moves around this curve, this origin of the z plane is circled exactly once. The number of encirclements is plus 1. Now think of the corresponding point w, that is for each point z here, I calculate w equal to z minus 1. That gives me a point in the w plane. Do that for each point on the curve, I will get a curve in the w plane. This curve is called the image of the original curve gamma, under the action of the function f, and because it is this gamma, points on gamma are being acted upon by f to produce points on this image curve. Sometimes this image curve is represented as f gamma. Actually, in your complex functions course, probably you have come across something like this, but at that time you may not have paid much attention to it. Well, now is the time to either revise it or pay attention, because this is going to be useful in our study of performance of a closed loop feedback control system, in particular investigations of stability of a feedback control system. So let us look at the simple problem of a mapping of the z plane into the w plane. That is, we have a function w given by f of z of a complex number or variable z. W also is a complex number, and let us take it to be the simple function z minus 1. Now, looking upon it as a mapping of the z plane into the w plane, we would like to see what the mapping does to a contour or a simple closed curve. I have chosen this simple closed curve here, which is the unit circle around the origin in the z plane. I have called it gamma, and I have chosen the orientation as shown by this arrow. The radius of this circle is 1. So, points on this circle, where do they go? In the w plane. We can choose a few simple cases. For example, take the point 1 plus j 0 or 1. So, if z is 1, what is w? W is z minus 1, so w is 0. So, in other words, the point 1 plus j 0 is mapped to the origin of the w plane. This is how we talk about it. A point in the z plane, namely 1 plus j 0, is mapped into a point in the w plane, namely w equal to 0, by the function f z. In this case, the function is z minus 1. Let us take another point, the other extremity of the diameter through the origin, minus 1 plus j 0. So, z is minus 1. So, what is w? W is z minus 1, and therefore it is minus 2 or minus 2 plus j 0. So, this point minus 1 plus j 0 will be mapped to the point minus 2 plus j 0. And in fact, you can now see what is going to happen. The action of the function is to subtract 1 from the number z. Now, subtracting 1 does what to the complex number? It does not affect the imaginary part, because you are subtracting only the real number 1, but it affects the real part. What happens to the real part? Since you are subtracting 1, the real part is reduced by 1. Therefore, you can see now that this circle gamma will be mapped into a circle gamma prime, or as I said, we can call it f of gamma. It is called the image of gamma under the function f. As this curve gamma is traversed in this counterclockwise direction, the curve gamma prime or f gamma will also be traversed in the counterclockwise direction, and the circle is mapped into a circle. And that is happening because this transformation or mapping is a very simple one. Namely, it is really a mapping which in mechanics you would call a displacement. The circle is displaced by 1 unit to the left, or in the complex plane there is a shift by minus 1. So, the circle goes into a circle. Now, the contour gamma encircles the origin once, as we saw earlier. Of course, one can see it immediately. What about the contour gamma prime? Does it encircle the origin of the w plane? Now, this is where one can run into a difficulty, because if you imagine that radius vector that I talked about going from the origin to a point on the contour, and then let the point move along the contour and see what happens to the radius vector, you will see that as one leaves the origin in this direction, the radius vector is pointing in the upward part of the w plane, whereas as you approach the origin at the end of your traverse, the radius vector is pointing in the downward direction of the complex plane, and therefore there is going to be a discontinuity in the orientation of the radius vector. Of course, the radius vector is never perfectly vertical, that is the tangent, but the tangent is not the same as the radius vector. So, if a contour passes through a point, then it is not so simple to talk about number of encirclements of that point on the contour by the contour itself, and so we will exclude this case. In other words, when talking about encirclements, we'll make sure that if we are talking about the encirclements by a contour of a certain point, that point does not lie on the contour. In this case then, because the function is w is z minus 1, and if we are looking at the encirclements of the origin in the w plane, then we must exclude the point z equal to 1, because z equal to 1 makes w equal to 0. So you have to choose a contour which will not pass through the point z equal to 1. So let me choose a contour which does not pass through the point z equal to 1, and that can be done by simply maybe shifting our entire circle already by 1 unit to the right. So this is the circle now, this is gamma, here is the point 1 plus j0, this point was mapped into the point 0, so now we have avoided it by not putting it on the contour gamma. In the w plane, what will be the image contour? This circle is shifted by 1, so the image contour will be simply the unit circle in the w plane. This is gamma prime. Now look at the following. The contour, the image contour, gamma prime or f gamma, how many times does it encircle the origin? In the w plane, we will look at the encirclements of the origin. How many times does gamma prime encircle the origin into the w plane? The answer is 1. Now look at the contour gamma. Of course, the contour gamma actually passes through the origin, so we will not talk about encirclements by gamma of the point origin 0. But look at this point 1 plus j0, which we avoided. How many times does gamma encircle 1 plus j0? The answer is 1. So in this case, the number of encirclements by the contour gamma of the point 1 plus j0 is 1, which is the same as the number of encirclements by the image contour gamma prime or f gamma of the origin of the w plane. Now is this a coincidence that there is one encirclement here and there is one encirclement here? Now this is not a coincidence, and we can check it for our very special function z minus 1 by taking one more example. For example, I can take the contour gamma which is different from this one, but I'll choose it in such a way that it encircles the point 1 plus j0. I can choose, for example, square. So if I choose a square in the z plane, let's say here is the z plane square whose sides are all 1 1 1 each, and this is the contour gamma, then what is going to be the image of this contour? As we have seen, we are going to shift 1 unit to the side of it will have to be 2 units and not 1, because I want the point 1 plus j0 to be inside. So it will not be a square with unit side, but it will be a square with side 2. So when we shift this curve by minus 1, we will get the square here of side 2. This will be gamma prime. The number of encirclements by gamma prime of the origin is 1. Of course, this is not a circle now, the contour need not be a circle, it simply has to be a closed curve, a simple closed curve to start with. So a square is a simple closed curve, and therefore gamma prime encircles the origin once. Whereas if you look at the z plane, this is the z plane, this is the w plane. In the z plane, gamma encircles 1 plus j0 once. Actually, what is important is not how many times gamma encircles the point 1 plus j0, but because the point gamma does encircle 1 plus j0, 1 plus j0 is inside the closed curve gamma. The function was z minus 1, w equal to fz equal to z minus 1. Where does this function become 0? At how many or at what points? This function becomes 0 only at the point z equal to 1. So this function has only one 0, and the 0 is 1 plus j0. The location of the 0 is 1 plus j0. The curve gamma encloses. Now this is the difference between encirclement and enclosure. In encirclement, we talk about sense, because the curve may be traced in one direction or it may be traced in the opposite direction, and the number of times the radius vector goes may be in the clockwise direction or may be in the counterclockwise direction. Therefore an encirclement is a number which may be plus or minus, or it could be 0 also. Whereas encloses there is nothing like 2 times 3 times. This point 1 plus j0 is enclosed by this contour gamma. Of course, gamma does encircle, if traverse this way, encircle it once. If I traverse it in the opposite direction, it will encircle it minus once. So encloses is what matters here. So the result here is that I have a curve gamma. There is a point which is a 0 of the function f, which is enclosed by the curve gamma. I have the image contour gamma prime. This image contour gamma prime encircles the origin the same number of times, as there are number of zeros enclosed by the curve gamma. Now this, of course, we are just verified by actual drawing for the simple function z minus 1. It holds for more general functions, not too general, but sufficiently general to be of use to us in our work with the feedback control system. Before I state the general result, let's take a look at one more example, and I'll ask you to go back and revise your complex variables, conformal mapping and things like that to get the answer. Now the function will be w equal to fz equal to 1 divided by z minus 1, not z minus 1, but 1 divided by z minus 1. Notice that this is what is called a rational function, because it's a ratio of two polynomials. The numerator polynomial is just a constant 1, the denominator polynomial is of degree 1. So this rational function has one pole, and the pole is at the point 1. Earlier the function z minus 1 had one 0, and the 0 was at 1. Now there is a pole, there is no 0. Now I'll choose the same contour gamma as before in the beginning, namely the unit circle. What do you think will be the mapping of this contour gamma, the unit circle in the z plane, into the w plane? Will it be a circle? The answer is no. The answer is that it will be a straight line. Not only that, here it's a simple closed curve. The image contour or the image curve is not a closed curve at all, but it's an open curve. And in fact, the open curve goes to infinity in both directions. What has happened is this curve gamma has passed through a point where the function has a limit or diverges to infinity as you approach that point, or the function has a pole. And as a result, what has happened is the image contour or the image curve is no longer a closed curve. Since it's not a closed curve, I cannot talk about encirclements and things like that. So this is a situation which also has to be excluded. The curve gamma should not pass through a pole of the function also. And now we are ready for the general result. Namely, we have a function w, which is a function of z, which is given by a numerator polynomial nz, n for numerator, divided by a denominator polynomial dz. These two polynomials could be of equal degrees, or they could be of different degrees. One of them may be a constant, as we saw earlier. We can therefore talk about the zeros of this function, namely they are the roots or solutions of nz equal to 0. We can talk about the poles of the function. They are the roots of the equation dz equal to 0. So in general, this function, rational function, will have a number of zeros and a number of poles. Now in the z plane, you can choose any contour, not necessarily a circle now, a simple closed curve. You can traverse it in either of the two directions, counterclockwise or clockwise. Let's say I once again select the counterclockwise direction, with only one restriction: the contour gamma should not pass through either a pole or a 0 of the function f. In other words, the contour gamma should be such that for no point z on it, nz will be equal to 0. Nz equal to 0 corresponds to zeros of the function f. So the contour gamma should not pass through such points. Also, it should not pass through point z such that dz equal to 0. These are what? These are the poles of the transfer function, or the poles of the rational function. So suppose I choose gamma such that it does fulfill this condition. It does not pass through any 0 of f, it does not pass through any pole of f. Now what is going to be its image in the w plane? Now that question is not easy to answer. I have chosen a contour which is not a circle anymore, so it is not something as simple as that. Therefore we cannot expect the image to be also something nice like a circle or a square and so on. But the following is true. This simple closed curve gamma will be mapped into a closed curve, not necessarily a simple curve, as we will see later on, into a closed curve gamma prime. I am going to show it as a simple closed curve, but it could be a closed curve which is not simple. It may intersect itself a number of times, as we saw earlier. Only to illustrate, I am showing it as a simple closed curve, but it will always be a simple closed curve. It will not blow up to infinity, neither will it pass through the origin in the W plane, because gamma does not pass through any 0 of f. So that's first thing. So it's going to be a closed curve. Now if it's going to be a closed curve, I can talk, and the origin does not lie on it, I can talk about the number of encirclements by this curve gamma prime. And what about the direction on gamma prime? That is determined by the direction of gamma. And it can happen that when I do it in the counterclockwise direction here, gamma prime may be traversed in the counterclockwise direction, but for some other functions it may turn out that it is traversed in the clockwise direction. So whatever is the direction of traverse, we have to stick to it. For the sake of standardization, let us say we traverse gamma in the counterclockwise direction. Now the following holds. Find out the number of encirclements of the origin in the W plane by the curve gamma prime if traversed in the same direction as the contour gamma. Now gamma we are traversing in the counterclockwise direction, so let us traverse gamma prime also in the counterclockwise direction. Now look at gamma prime only, find out what is the number of encirclements of the origin by gamma prime. In this case the answer is 1, and you can easily see it. Gamma was traversed in the counterclockwise direction, gamma prime also we are going to traverse in the same direction, and now the number of encirclements of the origin in the W plane is 1. Then the result is that this number equal to the following difference: the number of zeros of the function f inside the contour gamma minus the number of poles of the same function f inside the contour gamma. So it's interesting that this difference between the number of zeros of f inside gamma and the number of poles of f inside gamma, this difference is reflected in the number of encirclements by gamma prime of the origin in the W plane. And this result goes back to the French mathematician Cauchy, and it is sometimes called Cauchy's principle of the argument, because encirclement has essentially something to do with the change in the argument of a complex number. Remember, we think of the rotation of a radius vector whose length may be changing, but the radius vector changes its orientation. So it is essentially connected with the argument, not really with distance as such, and therefore it is called the principle of the argument, and this was first stated and proved by Cauchy. Now this principle of the argument is what we will make use of to determine the stability or instability or the closed loop poles of a closed feedback control system lying all in the left half plane or not lying in the left half plane. So this Cauchy's principle of the argument, which is what we will use, and this idea was used by the engineer whose name I already mentioned, engineer cum mathematician Nyquist. And so this has given rise to a test or a method of checking stability known as the Nyquist criterion. So this is what we will now turn to.